we'll try at some point to make up the lost time because, if not, I don't want to give you a short shrift of the course, but we'll try our best. We'll find at some point, I will circulate the notes trying to ask some possible times, but if this technology works, we can, even if there is a day that not everybody can come here, I can do it and make it available to you. So actually, before I launch into the main subject of today, which is doing one detailed example of calculating the distribution and its approximation when we are dealing with big numbers, so that we will be ready to eventually discuss a statistical meaning of concepts like temperature and entropy, etc. So today we'll be developing one model. But before doing that, I wanted to finish an example that we were discussing at the end of last class, and I said I can do it in a way which is a little bit different of what you can find in probability textbooks, although one of you, I believe, gave me a solution that is a sort of variation on what's usually in probability textbooks. Remember, the problem was a very simple problem that appears in many systems, particularly in quantum mechanics, where we have a bunch of independent particles in a system in which they happen to be equidistant. So this has energy 0, 1, 2, 3, 4, 5. So the distance between the possible energy levels are equidistant. An harmonic oscillator is an example of such a system, but doesn't matter for the purpose of our course, it doesn't matter. And what you have is n particles that can be in any of those levels. So they can be all here, or 2 here, 3 here, and 5 here, whatever. And you want to find how many microscopic systems are consistent with a certain total energy. You understand, the energy, if I have 3 particles, and one is here, and one is here, and the other is here, the total energy will be 2 plus 2, 4, plus 0, 4. So this would correspond to energy equal to 4. Imagine if you want the factor h bar omega or whatever you want. But so, for example, I would like to find how many configurations are there of 3 particles that have energy 4. And of course there are many, because you can have 2 particles here and one at level 4, or 2, 1 and 1, and so on. So a statistical problem is find what I call G of n, the number of configurations of n particles with total energy little n. Okay, and find the general expression for any capital N, any n. So what I was telling you at the end, this will be true in any system of non-interacting particles in which the total energy is the individual energies of the particles added up. In this particular case, in the case in which they are equidistant, of course, you can have many other variations, because if you have atoms and the level of energies in the atom are not equidistant, as you well know, it goes as 1 over n squared, but if you have a bunch of electrons in many atoms, well, then the sum will be a little different. And if you have those of you who have quantum mechanics, if you have a box, so a potential like this, and you have the levels here, the levels are not equidistant. There is a level here, one which has an energy 4 times higher, 9 times higher, etc. So the games you can play with the numbers will be different. This would be the simplest case. So the solution, well, first of all, let me try to do what I did at the end of last time, saying in certain cases you can guess. For example, G of n 0, the number of states with total energy 0 is only 1. Obviously, because there is only one way of having 0 energy is when all your n particles happen to be in level 0. And if you calculate G of n1, of course, you will have many possibilities now, because that means that all the particles have to have energy 0 except one of them that will have energy 1. And you have n choices, obviously, because any one of these n particles can have these, so there are n different states there. And if you have G of n2, now if you are counting all the ways in which the total energy can be 2, of course you have the n states in which all the particles are at 0 and one of them has energy 2, and there are n ways of choosing that. Or there are all the states in which all the particles have energy 0 and 2 of them have energy 1, which will be the way of choosing 2 elements out of n, which is the combinatorial n2. So this is n plus n minus 1 over 2, which happens to be n times n plus 1 over 2. You do the math, that's what you get. So that would be the G of n2. And you can keep going. For 3, you can also get it, because there is all the ways in which one particle can have energy 3, which are n ways, or all the ways of choosing one particle of energy 2 and one of energy 1, which will be n times n minus 1, because you have n ways of choosing the particle of energy 2, and for each one of those n minus 1 ways of choosing the particle of energy 1. Or you can have all the groups of 3, because you can have 3 particles of energy 1, 1, and 1, which will be the combinatorial n3, and you can sum that. So in principle you could, but it's clear that if n is a big number and n is 500, you are not going to get it just by counting 500 times all the combinations. So you need to do it in a way. So the way, or a variation of which you can find in most books, which is not the method I want to show you, but the way you will see it if you look in a book, in probability is by sort of inverting the problem. You say the following: I have n particles and n, if you want, quanta of energy. So imagine that you do the other thing around. You mind that each quanta of energy is a little ball. And now you have n ball. This corresponds to particle 1, particle 2, particle 3, and you have n of those. Okay, and now you have to decide this little n in how many ways you can distribute it there. And obviously you can put the n here, which would correspond to have particle 1 with energy n and all the others with 0, or the n particles here, or put 2 here, 5 here, and 7 here. But any way you do it, you are distributing n objects, little n objects. So it's the way of distributing little n objects into n boxes. You understand? Now a box represents one of my particles. And each of these n little balls represent now my units of energy. So this is the problem of saying in how many ways I can put little n objects in big N boxes. And the way most authors do it, they say they do something. There are several ways. This is called combinations with repetition. I don't want to go to the whole argument because that would be teaching probability. But there is one very intuitive way that says the following. Imagine that you do the following. You put all your units of energy here in a row. You have n of them. Okay? So I have little n, okay? So this is my energy. Let's imagine that I have two particles. Well, how can I split them? Well, I can split one of them. They are, and all these are indistinguishable, okay? Because these are units of energy. So it's just taking a line here and dividing and saying to the left, they are in box 1, to the right, they are in box 2. Okay? Because that's all you can do. If you put the line here, you're saying none in box 1 and all of them in box 2. If I put the line here, I am saying 1 in box 1, all of them in box n minus 1 in box 2, and so on. So it's the number of ways of putting a line
here, which is clearly how many, and including the possibility of putting it here if I want, because that would mean 0 in box 1 and n in box 2, or even putting it here. So it's the number of ways I can choose one line among n of these. So I pick n plus 1 spaces, the n little balls, and this one, and I find where among these n plus 1 I can pick my 1. So it will be n plus 1, 1, which is the number n plus 1. Okay, and if I have 3 boxes, well, then what I have to do is to put 2 lines here, and I will say one of the boxes to the left of the first line is box number 1, between line 1 and line 2 is box number 2, to the right of line 2 is box number 3. So these are all the way of choosing little n plus 2 and choosing among those where do I put my 2 lines. So this is the combinatorial. Okay? And in general, if I have n, I will get, if I have capital N boxes, what would I have? Now I have to put capital N minus 1 separators. Check that always I put how many separators, as many as boxes I want, minus 1. Because to the left and to the right I separate. So I will have little n plus n minus 1, combinatorial little n. No, combinatorial n, or little n minus 1. So that would be the answer. Understand among all the possible choices, I can put this choice. Oops. This is a possible choice, putting the 2 lines here. That's one possible choice, because that means, I don't know, 4 particles here, 0 here, and 7 here. So I am choosing all the possible spaces. That's why I say I have little n plus 2 spaces, and I choose in which ones I pick my lines. And the lines can be consecutive. There is nothing wrong with that. 2 consecutive lines means that there is one particular box that will have no energy. One particular particle in the other language that will be at the level equals to 0. Okay? So this would be one solution.
Shouldn't that be capital N minus 1? The common?
It's either this or n plus n minus 1, combinatorial n minus 1. No, sorry, I have to pick capital N minus 1. You are totally right. N minus 1 or little n, which is the same. Because the combinatorial 7-3 or 7-4 is the same. So you are absolutely correct, it's n minus 1. Let me make sure that's what I have in my notes. I have nothing. Yeah, n minus 1. You are absolutely correct. So, and sometimes this is called the stars and bars method, because they put little stars here and little bars, and they count how many bars can you alternate between the stars. So that's what you see in a textbook of probability. The way I chose to show it, which is actually not me, actually Kittel chose it, it's interesting because it might help us at some point along the line, which is a completely different method that has nothing to do with this, which is something very reminiscent to what some of you learned with me when we discussed generating functions, because it's in essence the same idea. And the idea is simply the following: to find the function f, which depends on the number of particles that you are trying to distribute, but it's a function of an arbitrary variable t, which actually encodes the solution you are looking. What do I mean by that? I am trying to find, I find this. Plus g of n, comma 2 t squared what I'm trying to find is these numbers. Remember, the g of capital N, little n. But I write a sort of infinite polynomial, if you want, of the function t, because this is a function of t. These are numbers, okay? These are the numbers I would like to know.
Why do we do this?
Because I am showing you another way of obtaining the same result, okay? So I create a mathematical function that somehow contains in itself the solution I'm looking, because all these coefficients are precisely the term n will be g of n little n t to the n. Okay? So one of the terms in this sum will contain precisely what I want to solve. You can tell me, how do I find it? Let's say I give you the function. How do I find it? Well, obviously taking derivatives. So if you need the g of n 0, all you have to do is to take the function f of n, f sub n, at t equals to 0. Okay? You write it at t equals to 0, you get that number. That's the g of n 0. If you need the g of n 1, what do? You have to take the derivative of this function with respect to t and calculate it at t equals to 0. Because when you take the derivative, this goes away. This term gives me g of n1, and all the other terms will contain factors of t that when I put t to 0 go away. So this is the derivative of f of n with respect to t at t equals to 0. Okay, and if I need the g of n2, what I have to do, assuming that I know the function, will be the second derivative of f n with respect to t twice at t equals to 0. Only that when I do that, this term goes away, this term goes away when I do two derivatives, and this term will give me the first time 2t and the second time 2. So I have to divide by the factor 2. Because what the second derivative gives me is twice this. And if I need the third term, I will get a factor of 2 and a factor of 3, so you immediately see where this is going. G of n little n will be the little n minus 1 derivative of this function with respect to t n minus 1 times at t equals to 0 divided by the factorial by little n factorial. Okay, the third derivative will be the g of n3 will be the second derivative of, no, here is the nth derivative, sorry. Is it? The nth derivative, absolutely, yes. It's the nth derivative of the function calculated and divided by n factorial. dn dt n times. Is that correct? Yeah, 1 over n factorial, the nth derivative of the function of f of n of t at n equals to 0. So you see, in principle, if you can calculate the function f of n, calculating what you want is an exercise of taking derivatives. You can tell me it's not a very pleasant way. Actually it is, because calculating derivatives is a much easier problem in many cases than counting states. So if I find the function fn of t, and I will show you that it's not that difficult to guess that function, then I just take n derivatives and I get the result I want. So the whole point is, now let me get the function f of n. If that method is going to work, let me. So let me start easy. Instead of getting the function f sub n of t, let me get the function f sub 1 of t, assuming that I had only one particle. Okay? Then the g of 1, 0 will be the number 1, but the g of 1, 1 will also be the number 1, and the g of 1, 2 will also be the number 1, Because if I have only one particle, the only way of getting energy 2 is put that particle in energy 2, and the only way of getting energy 3 is to put that particle at the level 3, and so on. So all these are ones. So the function f1 of t will be 1 plus t squared plus t cubed plus blah blah blah. Okay, because all these coefficients in front are the number 1. In the case of f sub 1, which is not what I need f sub n. But this function actually is the function 1 over 1 minus t. Okay, so f sub 1 is easy to get. The question is how to get the other ones. So let me do f of 2, and I am sure you will guess immediately what is f of t. So what is f2 of t? Is g of 2, 0 plus g of 2, 1 t plus t of g 2 plus g of 2, 2 t squared, etc., etc., etc. Okay? But let me convince you the following. What will be? G of 2, 0 will be the number 1. If I want energy 0, the only thing I can do is to put my two particles at level 0. G, let me use the old notation. G of 2, 0. G of 2, 1, how much is it? How many ways can I get energy 1? 2 ways. One particle in 0, one in 1. If I want energy 2, what do I get? Sorry, 2. If I want energy 2, I get 3 ways. 2 and 0, 1 and 1, or 0 and 2. Okay? And if I get G of 2, 3, there will be 4 ways. Okay? 3, 0, 2, 1, 1, 2, 0, 3. In general, you can immediately see that G of 2, any number n, will be the number n plus 1. Okay? So this sum that I have to do now will be 1 plus 2t plus 3t squared plus 4t cubed plus etc. etc. n minus 1. So no, n plus 1. Okay. Yeah. N plus 1. So 4 with t cubed and 5 with t4. So this is my function f sub 2. So you can say, who knows how to sum this series? And, well, we did it a few times or something similar in the course in probability. We'll have to learn how to sum this series eventually when we discuss Planck systems and so on. But actually, even if you don't want to do this, you can just realize that if you write 1 plus t squared plus blah blah blah, and you multiply that by the same, you get, and you open these two things, you just get that. Because you get the term 1, you get 1 plus t times 1, so you get 2t. T squared, you will get 3 terms, t squared times 1, t times t, or 1 times t squared, and t cubed, you will get it in 4 ways, and so on. So just multiplying these two things, which is 1 over 1 minus t to the power 2, gives me my f of 2. So f sub 1 was 1 over 1 minus t. F sub 2 is 1 over 1 minus t squared. Do I have to write what will be f sub 3? Yeah. But you understand that opening these factors, I am precisely doing what I want. You see, let me try to think for 3 particles. If I have 3 particles, and if I write this times the same factor times the same factor 3 times 1 plus t squared. You see, what I am doing is, and if I want to know how many ways can I get n particles, it's obvious. I can get 2 from here, let's say n is 7. 2 from here, 2 from here and 3 from there. Or I can get 1 from here. So all the ways of obtaining that are all the possibilities. Yes?
Why is the sum of 1 plus t squared, etc., 1 over 1 minus t? How does it sum?
Oh, that's calculus 1, my friend. The series 1, that's the harmonic series. 1 plus t squared, as long as t is smaller than 1, converges to 1 minus t.
Oh, t is less than 1, okay.
Yeah, yeah, of course. T has to be a number, so this function is defined for t smaller than 1, etc., etc. Okay, but you see that this is counting all the way. So in general, the function f sub n of t will be 1 over 1 minus t to the power n. So I have not proven it. If you want me to prove it, I would have to use induction and so on, but it's pretty intuitive that the function f of n is this. Okay? Once you have that, now you can go and do what I wanted. Remember, g of n, which was my problem, was dividing by little n factorial and taking n derivatives, little n derivatives of the function f sub n. So that's what I have to do. And the function f sub n, now I know it explicitly. So what happens when I take little n derivatives? Well, I am taking derivatives of the function 1 minus t to the power n. When I do the first derivative, I get the factor n, and I get, when I take the first derivative, this is 1 minus t to the minus n, I get a factor minus n, and I get 1 over 1 minus t to the power n plus 1, okay? Because this is minus n, and when I diminish the degree, I get minus n minus 1. And I have a minus, because there is a minus here, so this minus goes away, so I get the number n. That's the first derivative. When I take the next derivative, I will get a factor n plus 1. And again, the same game. I get a minus sign, but I have another minus from the derivative, so I get n minus 1, and so on. And I get here n plus 2, and so on.
What is that? 1 over n factorial times what's that?
The number n, that's from taking the first derivative. Now I have to take another derivative. I was showing you. So you will get 1 over n factorial, and I will get n. That's when I take the first derivative, n plus 1 from taking the second derivative, n plus 2 from taking the third derivative, all the way to n plus little n minus 1.
So that's n, and what's the thing afterwards? Like
N plus 1, n plus 2.
The line above.
The function,
That line.
sorry, I was rushing this, and I have still to take n minus 1 derivatives. I took the first derivative, I got the factor n. I take another derivative, and so on. So at the end of the day, this is what I get, because each time I get a derivative, I get the next integer after n. Check it, it's taking a derivative. Because when you take the derivative, you have minus n. If you subtract 1, you get minus n minus 1, which is minus n plus 1. And when you take another derivative, it's minus n minus 2, which is minus n plus 2, and so on. Is that what is bothering you?
Is there going to be like a negative 1 to the...
No, because each time you take a derivative, you also have to take the minus from here. So those minuses, each time you take a derivative, the minus cancels with the minus coming from here. So you see, that's the result. And if you look at this, what is this? This is n all the way to this number. If you multiply here by n minus 1 factorial, and here by n minus 1 factorial, what do I have? 1 times 2 times 3 all the way to n minus 1, n plus 1, n plus 2, all the way to this one. So I get n plus n minus 1 factorial divided n little n factorial, n minus 1 factorial, which is the combinatorial n plus n minus 1, n minus 1.
So that's
If you tell me that this method is very much complicated compared to the one statistical in probability books, okay, I agree with you. It's a matter of taste. It works. The other one also works. Books in probability normally teach you the other one because generating functions is not something they are interested in. We might use them later. But I wanted to show you that exercise. So now I stop this and we start discussing a little bit the story of. Okay, we start discussing. As I told you, I want to take one particular system in which I can calculate things with certain ease and where I can do approximations, because what I am after is trying to understand how these distributions change when n is a number of the order of 10 to the 23. That's what I have to do. So I'm not interested in just exact approximations, but how do they look in the case of big numbers? And in order to do that, the easiest thing is to consider what's called a binary system. A system in which each variable, each one of these n particles has only two states. You cannot get any simpler than that. Well, you can get one state, but if all the particles have one state, the system has only one state, right? So the simplest one is that, and so normally people represent that by a spin, because they say, the spin of an electron can point up or down. Or you can say, in a certain space I can have a 0 or a 1. Or you can say, in a certain material I can have here an atom of copper or an atom of zinc, and that's an alloy. So, systems in which in each place you have only two options. These are called binary systems. Okay? It's simple enough, but you will see that it has all the richness necessary to see what happens. So I will assume that each particle is either this or this. If you want, each time I write this, in your mind, think of the number 1, and each time I write this, think of the number -1, or 0, or whatever you want. But this is the point. I have n of these particles, so my system, any possible state of the system is something like this. Okay? A sequence of n arrows that either point up or point down. Those are the states. One microscopic state is one collection of these. How many of them do you have? How many different can you have? 2 to the n, right? Because this one can be in any of two states, and for each one of those, this can be in any of two states, and for each one of those, this can be in any of two states, etc. So the total number of let me call it microstates. In a minute you will understand what do I mean by macrostates. The number of microstates, the number of pictures like this that I can represent will be 2 to the n. If n is 10, if I have 10 arrows, I have 1,024 possible systems. So there are 1,024 possible states of my system. Plus, 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 minus, and so on. And you can pick the 1,024. Yes?
Does this thing have for order or no?
Yes, they are absolutely distinguishable. The first particle is here, but I know what your question is implying, and you will get an answer. But here, when I have a microstate, yes, this first arrow can be either a plus or a minus. If this one is minus and this one is plus, that's a different state. So each one is given by these arrows. Now, what is interesting is the following. If I write them, and there are many ways of writing this, so sometimes you can say the first particle, so particle number 1, can be in any of these two states. right? Either can be like this or like this. And particle number 2 can be in any of those two states. And particle number 3 can be in any of these two states. Why do I write it like this? Because if I open this product, I get all the possible states, right? In this case, I will get 8 possible states. I will get plus, 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 minus, etc. So this is a simple way of denoting every single state. In other words, I say if you open this product, you will get the 2 to the n possible states of my system. Among them, in this case, will be the plus, 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 minus. Obviously, you can see that there are 2 to the 3 or 8 in this case, but in general, you can have them. So this is what I have in my mind. This is a description of all the possible microscopic states in which my system can be. And yes, I am considering different ones. If this arrow is up and this is down, it's not the same as if this is down and this is up. The particles are clearly, I see the spins, I see how they are pointing. The number 1, 0, 0 is not the same as the number 0, 1, 0. It's a different number, okay? But if I only use zeros or ones, I can write only 8 numbers. 0, 0, 1, 0, 1, you know, the 8 possible numbers. Okay, so this would be just writing the states. But what I have in the back of my mind is that, although for the time being, I will assume that all these states can be there and none of them has any different property. They are all good for me. Eventually, I will try to establish a hierarchy of states. I will try to assign an energy to these states. How will I do that? Assuming that I put some sort of magnetic field there. Okay? What does it mean? If I put a magnetic field, as you know, a spin that points in the direction of the field will have one energy, a spin that points opposite to the field will have a different energy. The energy will be assume that the magnetic moment associated with each of the spins is little m. Little m has units of magnetic moment. Minus mb will be the energy of a certain spin in a magnetic field B. Okay? So if the spin point, if the field, it's minus, if you want, I assume, if you want just to do it the way you did it in physics too. This vector m can be plus or minus. Okay? So it can point in the same direction as B and the opposite, so you have two values. So if the spin points in the direction of the field, the energy is minus mb. If the spin points opposite to the field, the energy is plus mb.
The energy of the spin.
The energy of that particular spin. But since all these spins do not interact, if you want the energy of the whole state, will be minus m1 plus m2 plus m3, etc., plus mn b. Okay? Because the total energy is the energy of each of the spins. There is no interaction. These are non-interacting spins. The only energy they have is the energy of interaction with an external field. If I put b equals to 0, again, all the 2 to the n states have exactly the same energy, because nothing, all have energy 0. But the minute I put a spin, well, I put a magnetic field, the energy changes. But you see, what matters is a spin up counts as a 1, a spin down counts as a minus 1. So what matters is how many spins up minus how many spins down I have, because here what will I get? Let's say there are 7 spins up and 3 down. In the case of 10 spins, I will have minus 7 minus 3, it's 4. I will have minus 4 mb. Okay, so what matters for the total energy, and that answers a little bit your question, is doesn't matter. The number of spins up and spins down is what determines the energy. So if I am looking at energies, now there will be many states that happen to have the same energy. okay? For example, let's say that you have of your n spins, n minus 1 point up and 1 points down. Of course, there are n different ways of doing that, because the first spin might be the one pointing down, or the second one, or the third one. There are many states that correspond to what I just described, but they all will have the same energy, because you will have minus m times n minus 2b, because you have n minus 1 terms that are plus 1 and one term that is minus 1. So you have n minus 1 minus 1. So all these n terms that I just described will all have exactly the same energy. Okay, and of course they will be terms like this. This corresponds to having n minus 2 spins pointing up and 2 spins pointing down. Because n minus 2 is n minus 4, and so on. So you see that the energies will run from minus n minus 2, etc., all the way to plus n. Always multiplied by minus mb. But you know, the factor minus mb, I don't need to carry it. Imagine all this. This would correspond to the n spins pointing up. This corresponds to n minus 1 spins pointing up and only 1 pointing down. The next term will correspond to n minus 2 pointing down. I will have the term 0 here, corresponding to n over 2 spins pointing up and n over 2 spins pointing down, the state that is exactly balanced, like this. And this would correspond to all the spins pointing down, and so on. So you will get the sum n up minus n minus will range all the way from the number n to the number minus n. Okay? So you see how many states do I have? Clearly you have n plus 1 states. Okay? If you go from minus n to n, but in steps of 2, you get n or n plus 1, depending if you are odd or even. But let's say n is 10, so you have minus 10, minus 8, minus 6, minus 4, minus 2, 0, 2, 4, 6, 8. You have 11 states. So 11 possible energies. So all your 1024 spins that correspond to the 2 to the 10 will fall into 11 different groups corresponding to the 11 possible energies. Okay, so that tells you right away, if you have 1,000 states but only 10 levels of energy, that in certain levels there are many, many, many different states. Okay, not in this one. In this one, in the case when all the spins point up, there is only one way of all pointing up, which is all pointing up. But in the one where n minus 1 point up and 1 points down, you have n different ways of choosing which is the one that will be the rebel and point against everybody else. And if you have this level, 0, which is 50% of the spins up and 50% down, is all the way of choosing out of 10 objects, the 5 that are going to point down. So you see, in general, the number of states associated with one given level of energy will be the combinatorial n up, let's say. Okay, if n up happens to be equals to n, there is only one way. If n up happens to be n minus 1, it's the combinatorial n minus 1, which is the number n. And if n up is n minus 2, is the combinatorial n minus 2, which is the same as the combinatorial n2, which is n times n minus 1 over 2, and so on. So this is the number of configurations, of the micro configurations associated with one particular level of energy. Why? Because all it matters for the total energy is how many spins are up, not which ones are there. So this state and this state happen to have the same energy. Okay? Because it's 2 minus 1, and here also it's 2 minus 1. So these are two different microstates, but both are part of the state of energy, in this case, 1. Yes?
I think this might be a trivial question, but does that mean you can only have an even number of particles?
No, because you can have an odd number.
And how do you-
Then, that doesn't matter. Let's say n is 11. You can have one particle pointing up with combinatorial 11, 1.
So you could just never have an energy of 0 though?
No, the energy of 0 you will skip. That's absolutely correct. In that case, you are jumping by 2. So if this is minus 10, you go minus 10, minus 8, minus 6, 0. But if this is minus 9, minus 7, minus 5, minus 3, minus 1, plus 1. Yeah, absolutely. That is another way of saying that if you have an odd number, you cannot have 50 pointing one way and 50 the other. Always you will have one more. The most match you can get, the most balance you can get is having one more pointing one way than the other. Because obviously if you have n, you cannot divide. N over 2 is not an integer. That's a good observation. Okay? But from the mathematical point of view, it doesn't make any difference. You will see now where it makes a difference. So, what I am trying to emphasize now is that we have a system that has many microstates, but I can classify it in certain macrostates. For example, in the case of spins, when I put a magnetic field. I remove the magnetic field, all these 2 to the n states have the same energy. But if I put a magnetic field, well, then there are capital N or capital N plus 1 different energies, and I can decide, I can calculate how many of all my states fall in this energy, in this energy, in this energy. Imagine that instead of having spins, what you have is an alloy. Okay? This is an alloy, and in each place you can have an atom of species A or an atom of species B. A, B, A, B. Understand, it's pretty much the same idea. Every single choice of letters A and B is one configuration of the system. How many do I have? 2 here, times 2 here, times 2 here, 2 to the n. So exactly the same as before. And if there is no particular interaction between them, all will have the same energy. But if you assume that somehow there is a chemical affinity to particles of level of atom A, which is different from particle B, so the energy will be given by the chemical affinity of A times the number of particles of A, plus the chemical affinity of B times the number of particles of B. So the only thing that will matter is how many do I have of type A and how many of type B. So if I have A, B, 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 or A, B, A, B, A, B, it doesn't matter. As long as I have the same numbers of A's and B, I will have the same energy, and that will be an energy level. So you see, this problem is nothing different from the problem I described before. Let me see even if I did a numerical example. Yes, here I did it. Let me write. So I can have in my AB alloy, I will have, let's say, A1, B2, A3, A4, B5. So I'm putting a subindex to remember which particle is which. This is the first particle and happens to be A. This is the second and happens to be 2, and so on. And again, how can I denote all the possible states? By writing A1 plus B1 times A2 plus B2 times A3 plus B3, etc. If you open, and I have n terms, capital N terms, if I open any product here, I will get 2 to the n terms. One will be A, B, A, and the other will be A, B, 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 A, and so on. And we'll have all the terms. So exactly as before. So if I want to count how many, okay, I believe I should have given you a notation. Well, I'll come back to that and show you that this is the same notation. Let me just build the notation in the case of the spins, and then I'll come back to this example. Doesn't matter, but it's better doing it in the spins. Okay, so remember that I said that I can count all the states, all the energy of a state, how many, so let me write it again. I have my 2 to the n states that came from doing this, n times, okay? And if I open that, I get the 2 to the n. But I said they all fall into energy n or n times m, n minus 2m, n minus 4m.
Sorry, I don't understand the last thing. This step.
This is the same I wrote in the other board.
Yeah, no, the whole thing has the energy.
No. Among all these 2 to the n states, I will have some that will have energy n, corresponding when I pick all plus signs. There will be some that will have, I am writing here the energies, and I will go all the way to minus nm. This corresponds to the n choices up. This corresponds when I choose n minus 1 up and 1 of them down, and so on. My problem is, as I said, is to calculate precisely how many do I have in this state, how many in this state, how many in this state. In this state, we already said there is only one, because the only way of having n spins pointing up is to pick just this up, this up, this up. I don't have more than one choice. But when I have this, I can pick this up and this down and all the rest up, or this down and all the rest up, or up, 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 this term down, and so on. So I have, in general, I have the combinatorial n up. Let me call it, or n plus. I don't know what did I call it here in my notes. N plus, okay. So, one particular state, one of these choice, any choice will be given by the combinatorial n plus. If n plus is equal to n, I have only one state. If n plus is n minus 2, if n plus is n minus 1, which corresponds to this energy, I have the combinatorial n minus 1, which is the number n. And if this energy corresponds to picking 2 spins down, so I will have the combinatorial n plus, where n plus is n minus 2, and so on. So you see that we already wrote, without doing any mathematics, what is the degeneracy, so to speak, of any given state. What is the number of microscopic states consistent with the microscopic state, okay? It's just this combinatorial. But what I want to do now is to write it in a more useful way.
Can I ask a question?
Pardon?
Can I ask a question?
Yes, yes, yes.
So when we derive this, right, so if you sum all of them, we have the result before all the macrostates of the...
Okay, good point. So let me write it in another way, and probably this will clarify your question. So let me see that I want to write all the states. So for example, what will I have? Let's say I have 3 spins, okay? My system is of 3 spins. I have this, but I have this 3 times. So let me put it like this. And I understand that these are 3 copies, okay? And so when I open this, what will I have? I will have this term. I will have 3 different terms corresponding to 2 spins up and 1 down, corresponding if the first and the second are up and the third are down, or the first and the third are up and the second are down. So I will have 3 terms here, which is the combinatorial 3-1. Then I will have 3 terms corresponding to 2 spins down and 1 up, which is the combinatorial 3-2 times this. And then I have only 1 term, which is the combinatorial 3-3 of this. You see, actually, I am choosing, instead of the number of spins up here, I'm choosing the number of spins down, but doesn't matter. Okay? So you see, in essence, these 8 terms are here. Here is 1, here are 3 more, and the last one. Those are the 8 terms. Okay? So you can see immediately that what you can do is to write, if you want to write it in a compact way, what you can do is say that what you have is the number that will go here. Imagine that instead of having just 3 spins, I have n spins, where n is some very big number. Well, I will have this term with all the spins up times the combinatorial n0 plus the combinatorial n1 times the term where I have all up minus one of them is down, plus the combinatorial n2 times the term where I have all of them up and 2 of them down, and so on. Okay, but imagine that what I have in each term is n. So you see, what I am doing here is counting all. If I add this, plus this, plus this, plus this, I should get every single state. And if you have any doubt about that, one practical notation to write this is saying the following. This plus this to the power n is what? Is simply, I can write how many spins up, n plus spins up, n minus or n minus n plus, which is n minus, spins down. And here I will have the combinatorial n plus. And I sum over all values of n plus, going all the way from 0 to n, or all the way from n to 0. I don't know, here I did it starting from n. You see, here I'm counting all the terms.
Yeah, this is the binomial.
So, this term, and this is a binomial. This is the old binomial. So, this will be the term n0, which is the number 1, corresponding and having n arrows pointing up and no arrow pointing down. Then I will have a term combinatorial n1, corresponding to n minus 1 arrows pointing up and 1 arrow pointing down. Then the combinatorial n2, corresponding to n minus 2 arrows pointing up and 2 arrows pointing down, and so on. If you want to make sure that you have all the states, what you can do is imagine that these are the numbers 1. And if you sum, if this is the number 1 and this is the number 1, what you are doing is summing the combinatorial n plus 1 to the n plus 1 to the n minus n plus. Since this is 1, what you are summing is just the combinatorial. But, as Newton told us, this is the expansion of Newton's binomial. This expression is 1 plus 1 to the n. Okay, that's what Newton told us, that if you write n plus, and you sum over all values of n plus, something to the n plus, something to the n minus n plus, is something plus something to the power n. That's what Newton wrote. 1 plus 1 to the n is 2 to the n, so you know that you have all the states there. Okay? That you have found a way to write all the states. So, what I will do now